Every year, over 130,000 women in the United States itself are diagnosed with cervical cancer, and over 4,000 of these women will die from it. Cervical cancer is the fourth most common type of cancer for women worldwide, but because it develops over time, it is also one of the most preventable types of cancer. Although a wide range of factors can put an individual at risk for cervical cancer, we do not have a standard method to diagnose a woman who is at risk for cervical cancer. For example, if a woman who takes oral contraception and smokes regularly is at risk for cervical cancer, she would be able to eliminate those risk factors and change her lifestyle to limit her chance of getting cervical cancer. By leveraging machine learning, we can drastically reduce the number of women who are diagnosed with and die from cervical cancer by building a risk prediction model. In order to build a risk prediction model for cervical cancer, we can utilize an extreme gradient boosting algorithm, also known as an XGBoost algorithm. So what is an XGBoost algorithm? The XGBoost algorithm is a useful algorithm that can be used for both regression and classification tasks. It uses supervised learning and gradient boosting, which means that it produces a prediction model in the form of multiple decision trees. The algorithm works by learning from its errors in previous model predictions to come up with better future predictions. It trains weak models in a sequential manner. It builds a preliminary model on the training data and a second model on the residuals, which are the mistakes of the first model. This process is repeated until the maximum number of models have been created, or until the model provides accurate predictions. When training the model for this project, the model will be fed the input features including the individual's age, number of pregnancies, frequency of smoking, presence of an IUD, and if they have had an STD. The target variable or the output is the biopsy, which checks for the presence of cervical cancer. If the machine predicts that the woman should undergo a biopsy, but she does not have cervical cancer, she will know that she might be at risk and can act accordingly in order to minimize her risk. So the first step in this project is to import our libraries and dataset into our Jupyter notebook. So once we have installed and imported our libraries, we can go ahead and import our dataset as shown in the image in the slide. The dataset should be saved as a CSV file, and it will be linked in the description box down below. But when downloading my dataset, I named it cervicalcancer.csv and was able to import it as shown. The next step in building a risk prediction model is to conduct an exploratory data analysis, and this is crucial to getting rid of inconsistencies within the dataset. It basically requires removing duplicates, correcting errors, and also dealing with missing values. So first, we want to get some information from the data frame. So when we run cancerdf.info, we should get a table shown here, which shows us how many entries we have, or how many patients we have data from, and 36 different columns, which show the different features or inputs we have, ranging from the individual's age to the number of STD diagnoses they have. We can also get some statistical information about our data frame by running cancerdf.describe in the top left. And so in this image, for example, we can see that the mean age of the patients is about 26.8 years old. But if we look at the data frame without describing it by just running cancerdf, we can see that there are question marks under two columns, under the STD's time since first diagnosis column and the STD's time since last diagnosis column. And these question marks are placeholders for missing data or null data, and therefore we need to replace the question marks with NaN, which means not a number, in order to symbolize that these are null values. So to visualize the null values across our data, we can plot a heat map of our data frame with the given features. So we can set the heat map to 20 by 20, which just specifies the size of the heat map. And the white sections show the null values across our data. So as we can see, the STD's time since first diagnosis and STD's time since last diagnosis features have a lot of null values. So we need to remove those features from the data, and then we will have 34 columns in our data instead of 36. We also need to convert our data from object data types into numerical data types, as most of the features right now are stored as object data types. The third step in building our classifier is to visualize our data in order to find correlations between features. So we can start by obtaining a correlation matrix and plotting it as a heat map. And our correlation matrix shows us the correlations between different features, and the values that are closest to 1, which are represented by the white or really light colors on the heat map, represent a strong correlation, while the darker values, which are closer to 0, represent little to no correlation between the features. And as you can see on the heat map, there is a diagonal strip of values that are white and seem to have perfect correlation, because the same features align on the x and y axes, and identical features have a perfect correlation with themselves. So now that we have cleaned up and visualized our data, we need to prepare it before using it to train our model. As we have previously seen when describing and visualizing the data, the last four features, or the columns within the data, are Hinselmann, Schiller, cytology, and biopsy. And all four of these features are various diagnostic metrics, but since we are only trying to train the algorithm to predict the target variable biopsy, we only need to select the column, which is biopsy, as our target output. Then we can check our target shape, which is 858 as expected since we have data from 858 patients. Then we also want to check the input shape, and we get 858, 33 as we have 858 rows and 33 columns after removing the features that we don't need. Then we want to scale our data before splitting it into training, validation, and testing data. So using scikit-learn, we can normalize our input data or our features, and from scikit-learn, we want to import the standard scalar and the min-max scalar. We also want to instantiate an object, which is scalar, out of our class, which is standard scalar, and then we want to apply the fit transform method on our object, which is scalar, and pass along to the x to generate an output, which is the scaled version of x. And the last step before training the model is to split it into three categories, which are training data, validation data, and testing data. So the training data is simply used to train the model. We just feed the data to the model so that it can learn the relationships between the inputs and the outputs. So as the model is being trained, we want to make sure that the model is not overfitting the training data. And so we can use the validation data and feed it into the model as it has never seen the validation data before. We want the error on both the training and the validation data to be going down because we want the model to generalize, not memorize. However, if we see the error on the training data going down and the error on the validation data going up, that means the model is overfitting on the training data and is failing to generalize. The testing data is used after the model is trained, so after we have finished the training and iterations, we feed the testing data into the model, and the model will never have seen the testing data during the training, so it's completely new data. As we can see in the image here, the 0.2 in our training and testing data means that 20% of our data is going for testing and 80% is used for training and validation. And then the testing data set is split further into validation and testing categories. So as we can see, 50% of the data goes specifically into the testing and the rest goes to the validation. So the last step in the project is training and evaluating the model. So in order to train and evaluate the model, we first need to install and import XGBoost. We can establish our learning rate as 0.1 as that's likely a good starting point on our system. And we can also specify the desired depth of our classification tree as 5, which is basically the longest path from the base of the decision tree to the root. Here we can also specify the number of estimators on the number of models we are going to use, and here we set the number of estimators to 10. And it's important to note that we can increase the depth of the tree and number of estimators dramatically, but this means that our model is becoming more complex, and a problem that might arise is the overfitting of our training data, and the model might perform really well on the training data, but perform poorly on the testing data. So after we've established our learning rate and number of estimators here, we can fit the model and pass along our training data. And after running the code, we can see that we have achieved 97% accuracy on our training data, and we repeat the same process on our testing data. And we can see that the model has achieved 94% accuracy on the testing data. And given that the model has never seen this data before, we can say that the model has performed quite well. And after achieving this accuracy rate, we can go ahead and plot a classification report and confusion matrix, which show where the model did well and where it did poorly. And there you have it, a cervical cancer risk prediction model that can take in a patient's information and show their risk for cervical cancer. All of the resources I used will be linked down below, and thank you for watching.